cipher text. That means even by changing one bit or making all this AES cipher method uses 4 steps, that is transformation, permutation from original plain text. This is the plain text which has changed only one bit. Subbytes replace or substitute the normal key or normal date used in AES, maybe encryption algorithm and the decryption algorithm. Hello students, welcome to the next session of Network Security. I am Dr. Soumyashri from Department of Computer Science, Vidhyaashram, first grade college. Let's start this session with one more concept of the AES, that is the ciphers in the AES. The ciphers can be used. How does the cipher method or encryption and decryption is done using the concepts of transformation? This AES cipher method uses 4 steps, that is transformation, permutation, mixing and generating the round key. These 4 steps will be done in a particular order, or you can reverse it during the decryption. Encryption follows transformation, the diffusion or transformation or permutation, mixing, and in the final step we add the round key to get a cipher text from the plain text. The decryption will be reversal of the encryption, where you can shift the order of these steps. So how you can shift the order and how it decrypts the cipher text, let's look at that in this session. Alright, the AES uses 4 types of transformation for the encryption and the decryption. That is transformation 1, that is subbytes, then permutation, that is the subbytes, after that shift the rows, then mixing using the mix columns function, and lastly getting the round key using the add round key function. We use 4 functions here. One is subbytes, next is the permutation using the method shift rows, use the method shift rows. Once the shifting of the rows is done, position is changed. Next is mix the columns. Mix the columns, and the last step in transformation is add the round key. Add round key. We make use of 4 methods. For this, in decryption we have reversal procedure, that is inverse subbytes. Shift has inverse shift rows. Mix columns has inverse mix columns. And add round key has inverse add round key. So, can use these 8 functions in encryption as well as the decryption process. Okay. In the standard encryption algorithm, it is referred to as the cipher method, and decryption is referred as the inverse cipher. So, this session is all about knowing how does ciphering can be done or encryption can be done using these 4 methods. Okay. This is the original design of the AES cipher, where ciphers and inverse ciphers are designed to reverse the order of the functions. Okay, here we have the cipher key starting from W0 to W43, word 0 to word 43, total of 44 words with 11 round keys will be generated. It follows the methods. Plain text will be applied to add round key method, then uses the subbytes, then shift rows, then mix columns, and another add round key for the next round. Okay, this add round key generates the ciphertext, intermediate ciphertext, which is provided to next rounds. Like this, 10 rounds will be finished by adding the last procedure. Last function that we follow is add round key. The key is added in the end of each round, not in the beginning or in the middle. Only at the termination of a round, the add round key is used. Okay. When it is came to the decryption process, we get the plain text. Ciphertext is added, add round key, invert subbytes. Now order will be reversed. Order will be changed in this. Okay. We have invert subbytes first, then invert shift rows, invert mix columns, invert add round key. It is exactly shifted back, which gives the plain text at the end of the round 10 in the decryption process. So this whole is the decryption process. This whole is a decryption process, whereas this is an encryption process. This is an encryption process. Encryption and decryption will be reverse of each other. So it uses, decryption uses always the inverse function of these functions, which uses the same key but in reverse order. First round uses the word W40, 41, 42 and 43, and the last round uses the word W0, W1, W2 and W3. Okay, the order of the key remains the same, but the function will be reversed. Okay, so this is the original design of the AES cipher. Now we have the pseudocode for the AES 128 version, that is round key with 128 bits. So this is shown in this algorithm. This is the pseudocode we follow. Here we have the blocks of code. As we say in the beginning of the AES is a symmetric block cipher, isn't it? We are following the symmetric block cipher with this pseudocode. Like block to state will be converted to block to state, and add round key function is called to get the word from W0 to W3, which is applied for each round. So first, yes, input will get the subbytes from the S, then shift rows. If round is not equal to 10, only then mix the columns. If round exceeds the 10, stop the mixing. Add the round key in the last step. Okay. Then state to block. Get the ciphertext and convert it back to the block of 4 words or block of 16 bytes. Okay. So we have the out block in the encryption algorithm. The decryption algorithm will be exactly reversal of the encryption algorithm. Okay. Here we have the invertibility of subbytes and shift rows combination. Subbytes will replace the bytes. Subbytes replace or substitute the normal key or normal data in the block, and shift rows changes the position. That means both the functions are independent and they didn't depend on each other for their function or execution. So if you reverse the order of these functions, it won't make any difference in the final cipher text. So what we can do is, in decryption, we'll reverse the rows. That is, we first call the invert subbytes and next call the inverse shift rows. Okay, so we are shifting the order. In the same way, we are shifting or inverting the mix columns and add round key combination. The mix column and add round key will inverse. Mix column will change the position or mix the column with the interstate, mix the positions or mix the bits in the interstate, whereas add round key adds the round key to the block. That means even though position is changed, even though bits are exchanged, again in this also they are independent and doesn't depend on each other. So in this case also we can invert the functionality or invert the order of the execution of functions. So what we'll do is, first we call inverse mix columns and then go for the invert add round key. So this generates the round key. Okay, the order will be replaced. We have the alternative design of the cipher method where we are inverting the orders of the functions in a decryption algorithm, not in the encryption. In decryption algorithm, we are reversing the order, but the round key remains the same, only the order of the functions is replaced or exchanged. All right. Now, you have the alternative design that can be used here. Okay. So, cipher and reverse cipher in the alternate design. It is altered for a little bit. We get the add round key, subbytes, shift rows, followed by the mix columns and add round key. Everything will be in the order in an encryption process or encryption algorithm. We follow the inverse method in the alternative design. All right. Next, go with the changing key expansion algorithm. In the cipher method, instead of using invert round key transformation in the decryption or inverse cipher, the key expansion algorithm can be changed to create a different set of round keys in the inverse order. We are using key expansion instead of add round key during the reverse order to get new set of the encrypted algorithm or reverse order. Okay. The next thing is to know about an example in the AES cipher. In this section, some examples of encryption and decryption and key generation are given to discuss about the previous encryption and decryption algorithm. We have an example with a plain text, shows the ciphertext block created from a random plain text block using selected cipher key. We are randomly selecting the cipher key with this set, okay, 128-bit cipher key with the plain text, and we get the ciphertext using the AES algorithm. We have the set of input state and output state and the round key we use. We XOR these operations to get the output state. Same with the each of the round. This is the input state, goes with all the 4 steps in the transformation, then generates the output state by using the round key. Okay. Then we have other 4 words, combining them with performing XOR operation, combining, executing all the 4 functions, we get the output state in each of the round. This shows the first round, second round, third round, fourth, fifth, sixth. We follow the same up to 10 rounds. Same thing will be repeated up to 10 rounds with the same method. Okay. When it is combining or when it is decrypting, reversal of this will be done. In the first encryption, we combine the input state with the key and we get the output state. But in the reversal, it will be like this. So, keys will be combined with the output state to generate the input state. It is reverse of each other. Okay. Then we have another example which shows the state entries in one round, that is round 7 of the previous example. Okay, if you take the round 7, we have this example 18, 0A, B9, B5 combined with 62, 04, C5, F7 to get the output state. Okay, here we have the states in a single round. This is the input state. Okay, and after sub bytes, how you can get the state using the sub bytes function. After that, we follow shift rows function, generates this value. Then we have the after mix columns. Okay, once the after mix columns method is over, we get the output state like this. Okay, so this is how you can get the output state by following all the 3 methods. Okay, so first it will be add round keys. We use the round key set from this example and we use this to get the output state. Alright, so this is about the example. What happens when plain text is made of all zeros? If plain text all have zeros, using the cipher key of the previous example, it yields the cipher text like this. Okay, this is the cipher key and this is the cipher text 63, 2C, D4, 5E, 5D, 56, ED, B5, 62, 04, 01 like this. Okay, we get all the 16 bytes of cipher text from a plain text and randomly selected cipher key. Let's check the avalanche effect on the AES algorithm. Let's change only one bit in the plain text. Here you can observe this is the original plain text that we have used and we changed only the last 4 bits of the plain text, which generates entirely a new set of cipher text. This is the cipher text from original plain text. This is the plain text which has changed only one bit, that is avalanche effect. Okay, we changed only one bit in the last byte. The result shows that the diffusion and confusion has created entirely new set of cipher text and it affects almost all bits of, not all, almost every bit, but most of the bits are affected. These bytes, this byte, this byte, this word, okay, all are changed. This is remaining same and we have these values remaining same. Okay, now we have only 25% or 20% of the cipher text remained the same when it has the original plain text. When by changing only one bit, 80% of the cipher text has been changed. Okay, there is a great effect of avalanche effect on the AES cipher method. Okay, here we have the effect of using a cipher key for which all bits are zeros. So we have this set when we use cipher key is 0, plain text is non-zero and cipher key is 0. what is the difference when you have all zeros? So we get ciphertext like this 632C D45E. When you use plain text different and cipher key all zeros, again we get new set of cipher text. That means even by changing one bit or making all the cipher keys 0 or plain text 0, you can get series of changed cipher text in the AES cipher. Now what is the effect of attacks on this? Whether they can be able to get the ciphertext and the key from the AES, let's check with the cryptanalysis of the AES cipher. When you check with the security of the AES was designed for advancement in DES. Okay, most of the known attacks on DES were already tested on AES because AES is based on the principle of the DES. So all the tests that has been made on DES were also applied for the AES. When you check with the brute force type of attack, the AES is more secure than DES due to the larger size key. You can get 128-bit key or 192-bit key or 256-bit key. You have more number of key domains, which makes brute force attack difficult to get the plain text from the ciphertext and the key domain. When you check with the statistical attacks, so statistical attack says that numerous tests or number of tests have failed to do the statistical analysis because as I said, as I shown in the previous example, by changing only one bit, you are getting a whole new set of ciphertext where repetition of the text will be difficult to recognize by the cryptanalyst. Okay, there are some more examples like making the plain text all plain text zeros. When you have all the plain text zeros and cipher key a normal set of key, again you get new set of ciphers, isn't it? When you have plain text normal and all the cipher key zeros, then also you will get more number of or new set of ciphers. That means with each and every change in the cipher method, the AES becomes much more difficult for cracking by the statistical attackers. Okay. Again, AES has been proved that it is strong over the statistical attacks also. When you look at the differential and linear attacks, there are no differential and linear attacks that can happen over AES. Differential is using the differential polynomial, we get the ciphertext. Then linear attacks, straight away attacks on the ciphertext and the key to get the plain text are also failed in the AES cipher method. All right. When you look at the implementation of the AES can be implemented in any of the software, the normal security software, the normal hardware and firmware. You can use this encryption method and decryption method with a normal hardware configuration, with a normal security software and the normal firmware. The implementation can use table lookup process. Why do they need table lookup process? Is that use a well-defined algebraic structure. There will be a table lookup process to get the round keys. How we can get the round keys is by using the table lookup, because keys must not be repeated with each of the round, isn't it? Each round may be 10, 12, 14. Each round in encryption must get new set of keys. Who will going to check whether the key is repeated or not? The uniqueness of the key. How do you check this? So for checking that uniqueness of the cipher key, we make use of the table lookup process. So this table lookup process is going to get you the unique keys in the AES that gives you a well-defined algebraic structure. Okay. When you look at the simplicity and cost of the AES cipher, the algorithms used in AES, what we use in AES, like what are the algorithms we use or what are the functions we use is add the round key, sub bytes, then sub columns, then mix the columns, then mix bytes, then again add round key, isn't it? We use 4 functions. The algorithm used in AES may be encryption algorithm and the decryption algorithm are very much simple. It uses simple coding, isn't it? When you observe the pseudocode of the functions, you get to know that the logic we have used in the 4 methods of AES are very much simple, that they can be easily implemented. It is very easier to implement the cipher key using the normal processors. You need not to have the high-end processors or high-capacity processors, but the AES ciphers can work with the normal processors and a minimum amount of investment on the system. With a minimum amount of investment, you can get the implementation of the AES, isn't it? So we have the AES that is much more easier, simpler and much more stronger than the previous cryptographic method, that is the data encryption standard. We have 2 versions, that is the data encryption standard and the advanced data encryption standard. So data encryption standard, what is the disadvantages? It has only small set of key domains, isn't it? So this will be avoided by the advanced encryption standard. Okay. So we can avoid these things with the AES algorithm. Alright. So this finishes the AES cipher. Thank you.